FETs or BJTs. Both of them are transistors, right? Usually I came across people who asking where they should use a FET and where not to, and similarly where they should use a BJT and where not to. The answer seems very complicated to them because they think everywhere they are using a BJT, also a FET can be employed, and where they are using a MOSFET, it can be replaced with a BJT. Actually, they are right. In many cases, there is no special difference in choosing one of them to use. I mean, in many cases, you can design your circuit either using a BJT or a FET, but in some applications and in some certain conditions, you have to use a BJT and you can't use a FET. Similarly, in some conditions, you must use a FET and you can't use a BJT. Or in the best case scenario, using one of them is preferable to other. In this video, I'm gonna talk about 10 practical differences and show where you have to use, or it's better to use a FET and where to use a BJT. You won't want to miss the exciting conclusion at the end, right? Stay tuned. As I already mentioned, BJTs and FETs share a significant overlap in their application, especially when they are employed for switching loads at lower frequencies. By low frequency switching, I refer to the scenarios where the number of on-off state changes per second is low. For example, if you are going to switch a DC load at low frequency, it really doesn't matter if you use a BJT or FET instead of these DC switches here. In the scenarios like this, non-technical parameters like cost or availability in the market will be effective on your choice. Scenarios like that are not subject of this video, so it is better to not lose the time and move on to the first difference. Difference number 1, mechanism of control. In a very simplified way, FETs are controlled by voltage and BJTs are controlled by current. Yes, that's right. I know that this definition is a little bit difficult to understand because it doesn't specify when to use a BJT instead of a FET and vice versa. FETs are turned on when the voltage on their gate source is higher than a specific value called threshold voltage, and BJTs are turned on when the current flowing to their base is higher than 0. Suppose that you are going to make a circuit operating on 1.5 volts powered by these AA batteries. What you can do if you need an electronic switch or signal amplifier? Is it okay to use a MOSFET or you have to use a BJT? This is a good question, right? Since a BJT will be turned on with a base voltage above 0.7 volts, you will be comfortable using a BJT when the circuit is operating on these AA batteries because most of MOSFETs are triggered by a gate source voltage higher than 4 volts. I know there are some FET transistors that have a gate source threshold value lower than 1 volt, but the number of them is not much. By doing a simple search on online part seller websites like Mouser, you can see that the number of MOSFETs with a gate source threshold lower than 1 volt is not much, something around 7%. This means that you will be limited if you want to use a MOSFET in a circuit operating on 1.5 volts, while almost all of BJTs are fine with 1.5 volts. Anyway, the next difference is difference number 2, input impedance. MOSFETs have high input impedance and usually BJTs have lower input impedance, but before discussing high input impedance or low input impedance of transistors, I know that many of you will ask what exactly is input impedance itself. Let me explain. Suppose that we have this circuit operating here and it has one sensor input here. This circuit will respond to the values or voltages applied to the input. For example, it will turn on or off this load according to the voltages applied to the input. By applying voltages to the input will draw current, right? It is obvious. But the point here is that if you need to supply high current to the input to make this circuit sense the existence of the presented voltage here, it means that the impedance of this input is low. In contrast, the lower the current this input draws, the higher its impedance. So what? MOSFETs have high input impedance on their gate pin while BJTs have lower base input impedance, right? What it has to do with the application? The input impedance makes a lot of difference in practice. I'm going to explain. Most of resistive sensors like NTC or LDR or similar resistive sensors are set up like this. We have to put them in series with another resistor, I mean R here or R here, which usually have a high resistance value. Also, the sensor's resistance itself is high. So, if you want to use the voltage produced by the sensor, I mean V out here or V out here, to trigger a BJT, you will probably fail because the voltage at this point or this point is weak, meaning that it can't supply enough current. So it is likely that the voltage of the sensor here or here will drop to 0.7 volts, the trigger voltage of the BJT, and stick to that voltage. In contrast, if you want to use the voltage here or here to trigger a device with high input impedance like a MOSFET, it will be okay. Yes, that's right. In this circuit, the sensor voltage will be able to trigger a MOSFET without affecting the sensor voltage itself, and it will definitely work. However, using a sensor voltage directly to drive a MOSFET is not advisable. If you do that, you may face some difficulties. It was just an example. By the way, low input impedance is not always a bad thing, and it can be beneficial in some way in some rare cases. Anyway, let's move on to the next difference. Difference number 3, switching speed. BJTs have high input capacitance and MOSFETs have lower input capacitance. Similar to that of input impedance, I know that many of you will ask what exactly is input capacitance before discussing high or low input capacitance, right? Let me explain. Look here, there are some hidden parasitic capacitors inside any transistor. In a BJT, there are 3 of them. One between base and collector, which is called CBC. Another one is between base and emitter, which is called CBE. And the last one is between collector and emitter, which is called CCE. Similarly, there are some hidden parasitic capacitors around a MOSFET. The only difference is that there is a hidden node here in a MOSFET model called bulk point. Some of these capacitors are between the bulk point and the transistor terminals. Look, there are 5 hidden capacitors, hidden parasitic capacitors around a MOSFET. CDB, CSB, CGB, CGS, and CGD. There are some capacitances inside each transistor, right? Those hidden capacitors are actually intrinsic capacitors of the transistor. You may ask, so what? We were talking about switching speed of transistors. What those capacitors has to do with the transistor speed? When you apply voltage here to base emitter junction to turn a BJT on, these 2 capacitors, I mean CBC and CBE, will not allow the current flow to the base immediately, and they will draw current first to charge themselves. Actually, these 2 capacitors have to charge first to let the current flow to the base. This is a time-consuming process. On the other hand, when you stop applying voltage to the base emitter junction to turn the transistor off, the current flowing to the base will not stop immediately because there are some charges stored in these capacitors, and the current flowing to the base will continue until these capacitors are discharged. This process is time consuming as well. Similarly, in a MOSFET, when you apply a voltage to gate terminal to turn the transistor on, you have to charge these 3 capacitors first. I mean CGD, CGS, and CGB. And when you apply another voltage level to the gate terminal to turn the transistor off, you have to discharge these 3 capacitors first. Charging and discharging these capacitors is also time consuming. The higher the capacitance of the hidden capacitors, the more the time it takes to charge them, and consequently, the more time you need to turn a transistor on or off. I mean, the lower the capacitance of intrinsic capacitors, the faster the transistor will be. Since when you are working on a BJT, you have to deal with 2 capacitors, and when you are working on a MOSFET, you have to deal with 3 capacitors. You may think that dealing with 2 capacitors will be easier than 3, but no. Usually, the total capacitance of a MOSFET's hidden capacitors is much lower than BJT's 2 capacitors, so BJTs will be much slower than the MOSFETs in the same level in most cases, of course. Turning on and off a BJT will take more time compared to MOSFET in the same level. The point presented here was interesting, right? So it's worth it to like the video and subscribe to my channel, right? Thank you so much. By the way, let me clarify something. Actually, it is not only the intrinsic capacitors that makes BJT slower. There are some other technical reasons that are out of the scope of this video, so I'll simply skip them. Anyway, it is time to move on. The speed of switching will lead us to the next difference. Difference number 4, frequency rating. BJTs exhibit significant capacitance effect at the base terminal, which can slow down switching speed. In contrast, FETs typically have lower input capacitance compared to BJTs, which allows for faster switching speeds, particularly in high-frequency applications. It seems simple, right? But it is not that simple. There are some difficulties here. This is datasheet for IRF640 N-channel MOSFET. Look at this table in page 2 here. The total input capacitance of this transistor is typically 1600 picofarads, which is equal to 1.6 nanofarads. In fact, in this scenario, of course, it is really low and it is negligible in many cases. Not in all scenarios, but in many scenarios, this is negligible and low value. Now, look at this table in page 3. Here, the total gate charge of this transistor is typically 57 nanocoulombs in this certain scenario, of course. Also, the gate charge is negligible in many cases. To turn a MOSFET on, we have to let some electrical charge pass through the gate terminal to charge the capacitors, right? It means that some current will pass through the gate terminal. The next difference is about the charge current. Difference number 5, input current. We all know that once the input capacitors of a MOSFET are charged, there will be no need for extra charge or current to keep the transistor on. Actually, the current flowing to the gate terminal will be 0. This is true, but this fact leads many newbies to a misconception. Most of newbies think that the current flowing to the gate terminal of a MOSFET is always 0. This is not true. This is not always true. Think of a situation where we have to switch a transistor periodically. To clarify this misconception, I need the definition of current. We know that 1 ampere of current represents 1 coulomb of electrical charge moving through a specific point in 1 second. Since the input charge of the IRF640 was 57 nanocoulombs, we can calculate the current flowing to the gate. When you are going to turn the transistor on, you have to charge the input capacitors, so you have to let the charge pass inwards, and when you are trying to turn the transistor off, you have to let the charge to pass outwards. And also, we have to let 57 nanocoulombs charge to pass through the gate outwards to turn the transistor off 10 times per second. So, the total charge passed through the gate terminal will be 2 times 10 times 57 nanocoulombs, which is equal to 1.14 microcoulombs. If the total charge passed through the gate terminal is 1.14 microcoulombs in a second, the average current passing through the gate terminal will be 1.14 microamperes. Even though 1.14 microampere is still negligible in most cases, it is not 0, right? It is so nice. But what if you increase the frequency to 10 megahertz, for example? By the way, I have ignored many details in calculations for simplicity, okay? Let's continue. In this case, where the frequency is 10 megahertz, the current passing through the gate terminal will be 1.14 amperes, which is not negligible at all, and we have to do something about it. The action taken to care about the MOSFET's input current at high frequency will lead us to the next difference. Difference number 6. Biasing circuit. A BJT has a simple biasing circuit, but a FET needs more complex biasing circuitry because a FET transistor has to switch quickly. I mean, you have to do your best to charge or discharge the input intrinsic capacitors of a MOSFET as quick as possible, even when the switching frequency is low. I think it needs to be clarified. Regardless of the frequency of the gate pulse, we have to switch the MOSFET quickly. Look, this is a low frequency pulse and this is a high frequency pulse. No matter which one you are going to apply to the gate, you have to switch the transistor quickly. Actually, I'm talking about these rising and falling edges. If you look closer to these edges, you will find out that rising a low signal to high signal or vice versa is a time-consuming process. Rise time or fall time is referred to the time it takes to switch the voltage from low to high or high to low, from a low voltage to upper voltage in the case of rise time, or from an upper voltage to lower voltage in the case of fall time. These two pulses are in the same frequency, but if you apply the first signal to the gate terminal of a MOSFET, the MOSFET will turn on and off much slower compared to the time you apply the second signal to the gate terminal of the same MOSFET, because the edges here in the second signal are much sharper compared to the first signal. So the speed of turning on or off a MOSFET has nothing to do with the frequency of the pulses. It has something to do with the edges, fall time or rise time. Look, the difference between these two pulses is in the sharpness of the edges. The sharpness of the edges means the faster the signal turns from 0 to high voltage or high voltage to 0 volts. So the sharpness of edges is the key. Creating fast and quick transitions at switching signal along with some other factors will make the biasing circuitry of a MOSFET more complex compared to that of the BJTs. Actually, in many cases, MOSFET driver ICs are used for making those transitions quick and sharp. Now, you may ask about the importance of these quick transitions. You may ask why I have to make transitions quick and what are the consequences of ignoring that. Let me explain. Look at this MOSFET here. When the voltage at gate source is 0, the transistor is off, so the resistance between its drain source is almost infinite and the current passing through its drain source is almost 0. On the other hand, when the voltage at the gate source is high, the transistor is on, so the resistance between its drain source is almost 0 and the maximum current will pass through its drain source. Both of these two states are okay and safe, but think about the moment that the voltage at the gate terminal is rising, but it is not maximum value, somewhere between 0 and the maximum voltage. In that moment, the resistance between the drain source is not infinite, and also it is not 0. It is between 0 and infinite, say 5 ohms for example. Now, suppose that at that moment, the current flowing through the drain source is 10 amperes. 10 amperes at that moment. So the voltage across the drain source has to be 50 volts, and eventually the power dissipated at the MOSFET has to be 500 watts at that moment, which is terribly high. This is why we have to minimize the rise time and fall time to minimize the power dissipation, preventing the device from overheating. The lower the rise time or fall time, the lower the power dissipation, and the higher the rise time and fall time, the higher the power dissipation. This effect is more sensible at higher frequencies, because the transistor has to pass the intermediate area where the resistance of the MOSFET is in between more often. This phenomena is not only affecting the power dissipation, it also affects the current handling capabilities. Difference number 7, current handling. Because of lower on resistance of a MOSFET compared to saturation voltage of a BJT, a MOSFET when fully turned on will act like a resistor with very tiny resistance. For modern power MOSFETs, the RDS on can be in milliohm range or even sub-milliohm, and this will make them much better choice for high current applications. Anyway, the next item in the list is difference number 8, variability. BJTs or MOSFETs, which one is more variable between individual devices? Before answering that, let me clarify what I mean by variability. Look at this datasheet again. This is datasheet for IRF640 and N-channel MOSFET transistor. There are plenty of parameters here, but surprisingly, these values are not the exact values you will expect to get on a real device. Actually, each individual device will have a different value for each of these parameters. For example, both of these are IRF640 MOSFET transistor, but the value of these parameters will be different for each device. Now, this is datasheet for TIP41 and NPN BJT transistor. Also, there are numerous parameters here, and again, these are not exact values you will face in a real device. For example, values of these parameters will differ from a device to another.
This is called variability, and it is not an unusual thing in electronics. Almost every component has a datasheet, and values on the datasheet are not what exactly you will face in reality. But there is a subtle point here. Variability in MOSFETs is much more noticeable compared to BJTs. So BJTs are better friends for a designer, and you can count on BJTs more confidently than a MOSFET. Anyway, next thing I'm going to cover today is difference number 9, noise vulnerability. FETs, especially MOSFETs, are more susceptible to flicker noise and thermal noise due to the presence of oxide layer in the semiconductor material. On the other hand, BJTs are generally less vulnerable to noise compared to FETs due to their lower internal noise sources, lower input impedance, etc. While FETs are more susceptible to noise, they are still widely used in various applications, especially in high frequency and high speed circuits, where there are other advantages such as high input impedance and fast switching speed outweigh their susceptibility to noise. Difference number 10, non-technical considerations. It is not only technical parameters that makes you choose between a MOSFET and BJT. Sometimes parameters like cost or availability in the market makes you choose a particular transistor type. Also, there are some other parameters and differences that are not covered in this video because they are not as important as items discussed today. Anyway, we have reached the final moments of this video. Thanks for watching. If you want to join our community and stay updated with new videos, don't forget to like and subscribe. Until the next video, take care of yourself and have a good one. See you in the next video.